let's go ahead and continue. Now, I know it might seem a little weird. We're going to talk about counting, and this whole chapter actually is about counting, and you're probably thinking, Miss Kelly, I know how to count. I've done this before. But we want to come up with ways to count things that happen in a certain order, or maybe if the order doesn't matter, and so that's what we're heading towards. So you'll see that we won't just count things directly like 1, 2, 3, 4. We want to try to come up with a faster way to count something that is happening within some certain rules. So that's what we're working towards. We're going to start with the multiplication principle. So if we have two activities or two events that can be performed in n sub a or n sub b ways, so all we're saying is that the number of ways that we could do A is given by n sub A, and the number of ways that we could do whatever B represents is given in n sub B. If you perform them in succession, so if you did A and then B right after it, then the number of ways that you could do A and then B, would be given by the product of n sub A and n sub B. We're going to use this when we're trying to count something that happens in a specific order. So, for example, if you are picking out an outfit, you might pick your pants and then you pick your shirt, right? And so that would happen in a given order, and so we could use this technique for counting how many outfits we could come up with. Sometimes we're going to use a tree diagram to keep all of the possible options straight, and so we'll look at a couple examples here, and we'll use a tree or we won't use a tree. And the other thing to keep in mind is there's usually more than one way to count these things. So I'm going to show you one way, but if you think of a different way, as long as you are still counting all of the possibilities, then you're still going to get the correct answer at the end. So let's look at example 1 here. A professor must pick 3 students to complete 3 different surveys. There are 43 students in the class. How many ways could the 3 students be chosen? So the way that we're going to approach this is we're going to sort of think of this as there are 3 different surveys. So we have survey 1, survey 2, survey 3. So I'm just going to list survey 1, survey 2, and survey 3. And what I want to do is I want to determine how many people could complete survey 1, how many people could complete survey 2, and how many people could complete survey 3. Now remember, the professor has 43 students in total, and the professor is picking 3 students to complete, 1 for survey 1, 1 for survey 2, 1 for survey 3. So how many choices does the professor have for survey number 1? Well, they could pick any one from all 43 students. So they pick a student, and now that student has survey 1. Now, from the remaining 42 students, they're going to choose who's going to complete survey 2. And so we end up with only 42 students as a possible choice for survey number 2. And similarly, we have only 41 students for survey 3, because 2 students have already been assigned a survey. And so what we see is that the number of ways that this could be done would be given by 43 times 42 times 41. And this comes out to 74,046. Okay? And so there are lots of ways that we could do that, right? And so eventually this is going to lead us to a discussion of probability. So keep that in mind. We're going to be counting how many ways something can be done, and then ultimately we'll start using that to determine how likely an event is. Let's take a look at this second example here. We have a standard deck of 52 cards, and we want to know how many ways are there to draw a 3-card hand that consists of an ace, a king, or a queen. So first off, let me just give you a real quick reminder of what a deck of cards is composed of. First of all, there are 4 suits, and those are the symbols on the cards. So you could have a heart, you could have a spade, you could have a club, looks kind of like a little broccoli, and you could have a diamond. So there are 4 suits. Each suit has 1 card of rankings 2 to ace. Okay, so there are 13 cards in each suit. and the cards go 2, 3, 4, all the way up to 10, and then you hit a jack, queen, king, and ace. So there's only one ace of spades, and there's only one 10 of hearts. Every single card is represented, each number or each rank rather, we call these like the ranks of the cards. Each rank of card is represented once within each suit. There are 52 cards total. And the other thing we should mention is that spades and clubs are black, and hearts and diamonds are red. So that means that we have, we have 26 black cards total, and we have 26 red cards total. Okay, so we'll use a deck of cards for several examples, and your homework questions might ask you about that, and I might ask you about a deck of cards on a quiz or a test. So make sure that you're familiar with the breakdown for a deck of cards. It's a nice way to, sort of have some nice things that we can count. So we'll use a deck of cards fairly often. So what we want to do is we have the standard deck of 52 cards. So that means we have 13 hearts, 13 spades, etc. So we have every card represented, and we want to draw an ace, a king, or a queen. And it doesn't matter which order we draw them in. What we want at the end is to have one ace, one king, and one queen. So we're going to look at this problem in a couple of different ways. First off, let's consider this sort of using a tree diagram. That'll be the first approach that we use. So our goal is to get one ace, one king, one queen. So when I draw my first card, I could get an ace, I could get a king, or I could get a queen. And those would all be desirable things for our hand, right? Now, suppose I've drawn the ace, then at the next level, I'm hoping to get either a king or a queen, because the goal is to get an ace, king, queen hand. It doesn't matter what order I draw the cards, but I'm trying to get those three cards at the end. So now let's travel along the first branch. So far we have an ace, and then we have a king, and so finally I would need a queen. If I went along the second branch, we have an ace and a queen, so I would be missing a king. So we can go ahead and fill in the rest of the tree. Let's see, if we had drawn a king, then at the next level we would want either an ace or a queen. And if we had drawn the ace after the king, we would need a queen. And if we had a king and a queen, we would be missing an ace. And let's see, if we had drawn a queen first, then we need either a king or an ace. If we had a queen and a king, we would need an ace. If we have a queen and an ace, then we need a king. Okay? And so notice that if you look at any branch along the way, you will end up with an ace, a king, and a queen in some order, but you will always end up with those three cards. So now what we want to do is fill in all of the different, how many ways could we get that card at each step? So at the first step, how many different ways could I draw an ace? Well, there are 4 aces in the deck, so there are 4 ways that we could pull an ace. Same thing for the king and the same thing for the queen. So there are 4 options for me to pull a queen. Now, we've drawn a card by the time we hit the second level of branches. So now I'm looking at the sort of the second column here. But now I'm picking different cards, right? So my king, there are still 4 kings because previously I drew an ace. So I'll have 4 kings to choose from or 4 queens to choose from. The same thing is true for the second level. If I'm interested in finding an ace, well, previously I drew a king. So the number of aces and queens are unaffected. So we'll get 4 and 4. And the same thing for the last one. Once we get to the final branch, we'll have the same thing, right? If you look at the first branch, we had an ace, and then a king, and then a queen. I have not yet drawn any queens, so there are still 4 queens to choose from. So what we end up with is we have 4 choices for each card all the way across the board. So what we'll do is we will multiply across branches, and then we will add between the branches. So let's sort of show this on the first one. If I want to know the number of ways I can get an ace followed by a king followed by a queen, that will be given by 4 times 4 times 4. 4 times 4 times 4, or simply 4 to the third, okay? Which is 64. Let's look at the next branch. How many ways can we get an ace followed by a queen followed by a king? We can do this in 4 times 4 times 4, so 64 ways. Every branch should be giving us 64, right? Because each time we have 4 times 4 times 4. So we'll get 64, 64, 64, and 64. And so what this should be 64, not 6. And so what we need to do, we multiplied through the branch, and then now we add between branches. So we have 64, how many times? We have 1, 2, 3, 4, 5, 6. So we need 64 plus 64 6 times. So that will be 6 times 64, and this comes out to 384. So there are 384 possible ways that we could draw 3 cards and end up with an ace, a king, and a queen. Okay? Now, this is not the only way that we could count this problem. We could alternatively think of this, instead of looking at which card specifically we drew, ace, king, or queen, we could look at, well, how many cards could I draw in order to, and still, have an appropriate hand. So let's think of this sort of how we did the previous problem. I have 3 cards that I'm going to draw total. How many options are there for my first card? Well, card number 1 could be an ace, it could be a king, or it could be a queen. So there are 4 aces, 4 kings, and 4 queens. So there are 12 options for card number 1. Now, once I pick card number 1, that eliminates, so say I chose a king on that first card, then I can't pick any of the remaining kings. So for card number 2, whichever card I chose before for card number 1, that now has to be gone. So I'm going to have 4 cards of one face, and I will have 4 cards of another face. So for example, if we had chosen a king for the first card, then for card number 2, I can only choose from the queens and the aces. So there will be 8 cards remaining for us to choose from. And then now we'll choose card number 2, so that leaves us choosing card number 3. At card number 3, suppose we chose the queen for card number 2, then this would leave us with only the aces to choose from. So we will only have 4 cards to choose from. So we should have 12 times 8 times 4, which gives us the same value. So that's another way you can think of it. This one is a little bit trickier, I think, because you have to realize that the number of cards is going to go down by 4 each time. Okay? But yeah, so that's sort of the introduction to basic counting. Next week we'll be looking at using combinations and permutations to count more complicated quantities. Alright, until then.